In this section, we're going to go over some basic concept of probabilities. And probabilities is actually pretty interesting because it's probably the only branch of knowledge that owes its existence to gambling. So in the late 16th centuries, people who owned gambling houses would hire these leading mathematicians to calculate the chances of a person winning at a game. And these mathematicians actually realized that they could use these methods to solve other real world problems. So to get started, I want to introduce something called a probability experiment. And a very basic example of a probability experiment is a coin flip. And there's two reasons why. The first reason is that we have no idea what any individual outcome would be. In other words, we have no idea whether it's going to land on heads or tails. And the second reason is that even though we don't know what's going to land, either heads or tails, we do know that the outcome would be after a long series of repetition. Another way of saying this is that we know that the probability of getting heads or tails will be 50%. And there was actually an experiment that was done to kind of show this. So there was this experiment of a person, his name was John Kirich, and he tossed a coin 10,000 times and recorded each toss as a heads or a tail. So after 5 tosses, he saw that he got 3 heads and 2 tails. So if you compute the proportion of heads, so this will be 3 out of 5, this will be 0.6. So then, after 100 tosses, he would have 49 heads and 51 tails. And again, if we do the proportion of heads, this will be 49 over 100, which is 0.49. So then, after 10,000 tosses, he got about 4,994 heads and 5,006 tails. And again, if you do the proportion of heads, this will be 0.4994. And notice that these numbers are approaching something. If you keep going, it actually goes all the way to 0.5, which makes sense because the chances of getting heads or tails are 50% or 0.5. So this is something called the law of large numbers. And we're going to get into this more into this section. So let's go over some definitions. So a probability experiment is one in which we do not know what any individual outcome would be, but we do know how long the series of repetition will come out. Kind of like what we did earlier, we don't know when we flip a coin whether we get heads or tails, but after a long time or after multiple repetition, we know that the proportions of getting one or the other is about 0.5. The probability of an event is the proportion of time the event occurs in the long run as the probability experiment is repeated over and over and over again. Something you want to note, and this is really important, is that the probability is always between 0 and 1. The reason is that you can't be over 100% sure of something. So that's why we have to restrict it between 0 and 1. And the probability of 0 means that the outcome is impossible, and the probability of 1 means the event is certain to occur. The probability of 1 is just the probability of 100%, and then 0 is just 0. And then one thing we're going to talk about a lot in this section is sample space. So a sample space contains all the possible outcome of a probability experiment. A sample space denoted by an S, and is written as a set with curly brackets. So this is really important. We're going to talk about sample space a lot in this section and the next section. So I want to go over an example of what a sample space is. Let's consider the table below, which is the list of some example of experiments. We want to find the possible outcome and the sample space. So for tossing a coin once, we know there's only two possible outcomes. We either get heads or tails. Now we want to write this as a sample space. So we have to denote this by S and then write it as a set with curly brackets. Now for rolling a die once, we know a die only has 6 sides, so the outcomes are 1 through 6. And so writing our sample space, we denote it by S and then write 1 through 6 as a set with curly brackets. Tossing a coin twice is different than tossing a coin once. You have to think about all the possibility when tossing a coin twice. So the first time we could get heads, and the second time we could also get heads. We could also get heads tails, tails head, or tail tails. So these are all the possible outcome. And we have to write this as a sample space. We could play a lottery, so we could either win or lose. And lastly, we could take a test. We could either pass or fail. So this is an example of some sample space. Sometimes people get a little bit confused when thinking about tossing a coin twice or even rolling a die twice, because people have a hard time of thinking of all the possible outcome that I could have. And so what people do is something called a tree diagram. So what a tree diagram does, it kind of helps you visualize all the possible outcomes when dealing with example like this. So let's try it. So let's say you toss your coin once. So there's only two possible outcomes. You either get a heads or tails. So let's say you get heads and you toss your coin twice. So this is the second toss. So again, there's only two possible outcomes, heads or tails. And again, for this side, so you get tails, you only have two possible outcomes for the second toss, heads or tails. So now you can kind of follow the line. So we have heads, 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 tails, tail, heads, and tail, tails. And if you notice, if you make this your sample space, is exactly what you wrote down from the previous example. So tree diagrams are really useful tools to identify your sample space. So if you have trouble kind of visualizing what your sample space might look like, try drawing a tree diagram and see if that could help. All right, next thing I want to talk about is a probability model. So let's go over some definition. So an event is an outcome or collection of outcomes from a sample space. Events are usually denoted with capital letters. A probability model for an experiment consists of the sample space along with the probability of each event. And notation-wise, this is very important. Let's say if A is an event, notice that it's a capital letter, then the probability of A is denoted by this. So it's P, open parentheses, A, close parentheses. So in words, this reads as the probability of A. And we're going to do some examples with this. So there was this group of people, and some were in favor of genetic engineering and some were against. And we want to select two people randomly and we want to ask if they're in favor or against. So the first question is, how many distinct outcomes are possible? So let's denote F as in favor and A as in against. So people who are in favor and people who are against. So our sample space should be FF, FA, AF, and AA. All the possible outcome. But let's say this was a little bit hard to come up. And what you could do is draw a tree diagram. So let's say you select the first person and there's only two possibilities, person who's in favor and person who's against. And then the second person, do the same thing and you want to follow the line. So this would be favor, favor, or FF, FA, AF, or AA. So this is your sample space. And notice that this is exactly what you wrote down for the first question. Next, we want to list all the outcome included in each of the following events. So what I would do is rewrite the sample space around here to make it a little bit easier. And the first question is, both persons are in favor of genetic engineering. If you look at our sample space, there's only one possible outcome that could happen. So here, FF will be denoted. And then B will be at most one person is against. So at most means 1 or 0 people are against. So this will be FF FA, and AF. And the third question is exactly one person is in favor of genetic engineering. Here, we have 2 possibilities, AF and FA. Last, at least 2 people are against. So at least means 2 or more people are against. And if you look at our sample space, there's only 1, which is AA. Now that we had some examples in practice with probability models, we want to actually compute these probabilities. And there's actually a couple of ways you could do that. So if your sample space contains equally likely outcomes and the event A has some number of outcome K, then the probability of A is just the number of outcome in A over the total number of outcomes. So there'll be K over N, where N is the total number of outcome. And remember, when something is equally likely, is that everything in that outcome has the same chance of getting picked. Another way you could compute your probability is actually using your relative frequency. So the probability of A will be the frequency over the total number of frequency. So there's a little reminder of what relative frequency is. It's just proportion. And lastly, another thing you could use is called the empirical method, which consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of that outcome. So we're going to do some example of all 3 methods. Another thing you want to note is that expressing a probability, you can do it as a fraction, as a decimal, or as a percentage. Another thing you want to know is that if you want to do a decimal, it's very common, again, in stats that you use 3 decimal places. We also have something called the law of large numbers, which we went over. As the sample size of an experiment increases, the relative frequency of outcome gets closer to the actual true values. And I want to talk something about an unusual event. So an unusual event is one whose probability is really, really small. And typically, the cutoff point is 0.05. Sometimes in other textbook, it's actually even lower, 0.02. But with this textbook, we're just going to cut off with 0.05. So any event with a probability that is smaller than this number is considered unusual. So that's what it means. So let's do a couple examples. So in the first example, we flip a coin and we want to know the probability of flipping a head. And notation-wise, this is P of H, where H is our event, which is flipping a head. So the whole thing is, in words, probability of flipping a head. And we know that this is 1/2 or 0.5. Another thing you want to note is that if you write something like P of 1/2, this doesn't mean anything because 1/2 is not an event. So this does not mean anything. Just a little note there. Next, what if we flip a coin twice? We want to know what is the probability that we flip at least one head. So I would recommend writing down our sample space. And we've done that several times throughout this video. So our sample space is HH, HT, TH, and TT. So we want to look at the ones that have at least one head, which are these 3. So then the probability of flipping at least one head is 3/4, or 0.75. Next, let's say we know roughly how many boys and girls are born each year in the United States, we want to approximate the probability that a newborn baby is a boy. So the first thing you want to do is take the sum of all the boys and girls that were born in the United States. So this will be 2,046,935 plus 1,952,451, which gives us 3,999,386. So the probability of a newborn being a baby boy is the number of baby boys over the total sum of newborns, which gives us 0.51181, but we have to round to 3 decimal places. Next, let's consider some relative frequency. So here we have a table, which is a result of surveys with 200 people were asked how they traveled to work. So the total is 200. And you want to find the probability that a random selected individual carpools. So you can think about this as relative frequency. So the probability of a person carpool is 22 out of 200, which is 0.11. And similarly, what is the probability of someone randomly selected works from home? Well, this is just 9 over 200, which is 0.045. For this example, let's consider a family with 3 children and assume the outcome child is a boy and child is a girl are equally likely. We want to determine the sample space. For this one, it's going to be a little bit tricky, so I recommend doing a tree diagram. So we know the first time will be boy or a girl, and then the second selection, again, boy, girl, and this time we'll have a third layer. So this part is a little bit different. Usually we have 2 layers, but now we have a third layer. And we kind of do the same pattern we did earlier. So this would be boy, 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 girl, boy, girl, boy, and then you kind of just keep going with the pattern. So this will be boy, girl, girl, then girl, boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. So our sample space will be all these outcomes. So again, if you have trouble identifying what your outcomes are, it's best to draw a tree diagram. Once we have our sample space, we could write our probabilities. So what is the probability that exactly one child is a girl? If you look at our sample space, there are 3 situations when that happens. So this will be 3 out of 8, which is 0.375. Next, we want to find the probability that none of the children are boys. If you look at the sample space, we know that the probability of that happening is 1 over 8, or 0.125.